I'm going to create a new flavor of conservation laws in physics through a quantum mechanical definition. Okay, so not only do we need conservation of energy and momentum, but we're also going to have to conserve probability of these self-conjugate operators that we've defined in the previous episode. And so what we're going to do is we're going to define something which will come from taking the variation, just taking the partial derivative of the state of the system with respect to the wave function and calling this an operator. Okay, so we're going to define this operator by the differentiation of the wave function with respect to time. And this factor here is introduced for consistency with the classical limit, of course. Okay, and so what we're going to need to do is say that this operator first. We're going to be working within Hermitian statistics. So this operator is Hermitian. Okay, this operator is Hermitian inherently, and this is a necessary condition, of course, to conserve this squared modulus of the wave function integrated throughout the element in configuration space. Sets of unity, of course. Okay, but that's just something just to remind yourself. And so the time derivative then of the integral of this self-conjugate operator, or of the self-conjugate, of the conjugate of the state times basically just the squared modulus of the state. So if we take the time derivative of this, what we can do is then use the Leibniz rule for differentiation and just giving it to, it's basically like an inverse product rule. But I'm going to take the partial derivative of the conjugate of the state times the product of the conjugate with the partial derivative of the state itself. With respect to this, and we're going to set this whole thing equal to 0. Okay, and when we do that, this is the requirement of this operator to satisfy hermitativity, okay? By the very definition, for this operator to satisfy hermitativity. And if we substitute the wave function in for its conjugate, we can show this, okay? But essentially, this is how we're going to define hermitativity. And to identify this physical quantity, okay, we want to identify this physical quantity which has this property. We want to examine the quasi-classical function, which is essentially that we have some amplitude, which is scaling this wave function that has a phase of the action quotiented by the Planck's constant, or the reduced Planck's constant. And hence, of course, we're going to assume that this amplitude is not varying with time, or that it's at least varying with time very slowly. And so the time derivative of this then, with this semi-classical limit, would then just be the time derivative of the wave function. Sorry, can you see that? Yes, you can. Time derivative of the wave function is equal to IH hat over the wave function again, okay? Over the wave function. But the partial derivative of ds by dt comes out, okay? And then whenever you compare this to the wave equation here, if you were to compare this to the wave equation, in the classical limit, the action of the operator, so whenever we push the classical limit, which is that a prime goes to 0 and h bar goes to 0, we get the exact classical limit that we get, that is multiplication by negative ds by dt. And in classical mechanics, of course, this corresponds to Hamilton's function. Okay, that's Hamilton's function. And thus, we identify this operator as a Hamiltonian operator. Because, in the classical limit, we necessitate that we get Hamilton's function by comparing the structure of the wave equation. Okay? By comparing this necessary thing and solving for this. Okay? And we get that. So that's what's really important whenever we define why we call this a Hamiltonian operator. Okay? So now we've defined the Hamiltonian operator from first principles. Using merely the Hermitian statistics, or the Hermitian matrix statistics, as well as this idea of a wave function or a wave equation. Okay. Now what we need to do is show that we can differentiate these operators with respect to time. All right. And so just as we had the physical quantity f, okay, let's define this as a physical quantity. Okay, physical quantity. We can say that at a value at one instant, may not have a definite value at the next, and so we can't really define this, differentiating this in some interesting way. And so what we need to do is we need to define the operator, okay, the time derivative operator, or the operator for the time derivative of f, okay, of the change of that physical quantity, such that its mean value. Such that the mean value, so we need a statistical definition, the mean value of the physical quantity is going to take on the time derivative of the mean value itself, okay? All right, so we're going to define it in such a way that we have this. And so starting now with the mean value of f, that is, of course, it's going to be defining what it means for an operator to act onto a quantum state. When we do this, and we differentiate the operator with respect to time, so if we were to differentiate this whole thing with respect to time, this is a total derivative, okay? Total derivative is going to do the Leibniz rule, and it's triple Leibniz rule, okay? And so let's work this out. So we're going to have that this should be the integral of the quantity of psi star dt times these guys, plus the quantity of psi star del f hat by del t times the state, plus psi star f hat times psi del psi by del t. All of this integrated throughout time. Okay? No. Integrated through the volume. Through the configurations of this, through the volume of the configurations that it could possibly be in. Okay? And then so what we're going to do is we're going to substitute the wave equation here. Alright? So the wave equation, is going to be substituted into here. And so when we substitute this in, we can then have that the derivative of the average value of the physical quantity should be equal to psi star times the quantity, or this is going to be a new operator contained within here. Let me make sure you can see that. Yeah, you can. You can see up to... Can you see up to there? Yeah, you can. Perfect. There's enough space. It's going to be the partial derivative of the operator with respect to time plus I h bar times h, the Hamiltonian operator acting onto the physical operator minus the operator acting onto the Hamiltonian integrated through dq here again. And so what this is really, we're going to define this quantity. Really what's happening is this commutivity relation, all right? And so in quantum mechanics, we refer to this as the commutator, okay? Within this, the time derivative of the actual average value. And so then what we can do is by definition then, that the f dot hat, by definition the operator in parentheses, then should be equal to this new f dot hat that has the time derivative of the operator plus I h bar times the commutator f of the Hamiltonian and the f hat quantity. And so this whole thing here is what we now define as f dot hat. Okay, and what this means. Well, first of all, we have a new equation of motion. This is called the Heisenberg equation of motion. This is the Heisenberg equation of motion right here. And it comes from the f dot hat operator. So it's an operator equation, okay? And this physical quantity is said to be conserved. We have a new conservation law. If its operator does not explicitly depend on time, okay? And if it does not explicitly depend on time, so if this is 0, and if it commutes with the Hamiltonian, so that it by definition can conserve the Hermitian statistics of the system, okay? And so that's kind of what we have now. And let's talk about now this idea of stationarity, or the stationarity of a state, okay? What does it mean for a state to be stationary? Well, I'll give you a hint, or I'll just give you the answer. We have a definite value for its energy. We have resolved it in time, so that we know for sure what the energy levels that we're reading. Those are what we would call stationary states. So let me get this here. All right. So stationarity. Okay, stationarity. What we would say for a closed system, or system in a static external field, the Hamiltonian is not an explicit function of time. And so, of course, we're going to say that any operator, and specifically the Hamiltonian operator too, because it's any operator, it commutes with itself. Okay? And so the Hamiltonian is a conserved quantity. This is conservation of energy. This is a new formulation of conservation of energy that just depends on the commutation of the operators. And so what we're going to say is that with states with some definite value, or some definite eigenvalue of energy, these are called stationary. Okay? And so the wave functions then are the eigenfunction of the Hamiltonian. It's going to satisfy this operator equation that gives us the eigenvalues of the this is the eigenfunctions, and then the eigenvalues are going to be spit out from the Hamiltonian. Okay, and so the time dependence of these states is solved. Okay, if we were to differentiate the eigenfunctions, they should inherently, or if we wanted to solve for that energy state, this will look something like the separation of variables, okay? And it should give us some spatial part of a wave function, which we're going to denote as little psi from now on, okay? This is the spatial part times some temporal part that evolves with time, okay? So we have some spatial part and basically we're solving this equation by separation of variables, okay? And so the spatial part of the wave function psi n, and sorry, this should have this spatial side of the wave function is a eigenfunction as well. Okay, and so it's going to be this is going to be determined by the time-independent Schrödinger equation. Okay, with the spatial eigenfunctions that will then also give us the energy levels that we need. Okay. That are going to spit out the eigenfunctions of the energy, or the observable energies. Okay, and so all observable properties are constant in time. And so actually the entire state of the system, because all the properties are constant in time, should be equal to all of the spatial wave functions. Okay, so the entire probability and the mean value of any time-independent time-independent operator. So we'll say that here's the operator and it's time-independent. So then the mean value will be equal also to the spatial parts of the mean value of the operator as well. Okay, so we have this too. That's also another thing that we get for free. We're going to say an energy level is said to be degenerate, so E sub n is said to be degenerate. Oh, let me get a new chalkboard. Chalk piece. It's said to be degenerate if it corresponds to more than one distinct stationary state. Okay, so if there's more than one, more than one stationary state. Okay, so So there's just more than one stationary state taking that energy level. It's said to be a degenerate energy level. Okay, and this actually appears in symmetry, or in the symmetries of the system, and it arises because of those things. But we're going to have a whole chapter dedicated to symmetry, so don't even worry about that. But we just wanted to introduce the idea of a degeneracy, that we can use it later. Okay, and so inherently, now that we have this idea of stationarity, we can now talk about matrices, the matrix mechanics, or the Hermitian matrices. How can we change the representation of our the quantum mechanics that we've built so far? Okay, how can we represent these energy levels in a matrix way? Or I guess the word would be matricial, matricial. We're going to represent it with matrices. Okay, so choose stationary states. Okay, as a basis. So it is a basis, okay? And we can expand the wave function then, okay, the total wave function, of course, as the A sub n of the states, okay? And so the mean value of the quantity can then be the nth rows in columns of A star m times A m. Fmn, this more larger matrix as a function of time. Okay, so we would say that the set of quantities Fmn are the matrix. These are the matrix elements of F, of the physical observable. And so then we can just define this. All the matrix elements should be given, or should satisfy, the integral of the complex conjugate of the mth rows of the state times, or with the operator acting on the state itself on the nth columns, dq integrated throughout the volume. Well, this should give us, of course, the Fmn matrix times the difference between those energy levels in the columns and the rows times time quotiented, of course, by Planck's constant. And then we can rewrite this in a better way, which is e to the omega n, which is e to the omega n, m in t, where this is now, this part here, this would be some frequency of the temporal, this would be some frequency defined by the differences in the energy. Of course, with the omega, but this matrix of F, okay, this time-independent part here, F, and the time-independent part of F m n is what we're going to call this the matrix of the physical quantity in the energy representation. In the energy representation. All right? And so the matrix elements of the operator product, okay? So if we were to have the matrix elements then, we have F hat and some G hat, if we had some product between operators, this would be given by just a normal kind of multiplication rule for the matrix. So the matrix itself of these operators would then just be, of course, F m K, G, K, in. All right. So that's kind of how you would just basically do the normal kind of method for multiplying matrices. But what happens? I'm writing this like crap. Okay. There we go. What happens is that now we can define, well, what was that fancy kind of Hermitian operator that we were talking about earlier, where we said F hat is equal to F hat dagger. Well, F hat dagger necessarily kind of implies, now in the matrix, or the energy representation, that the matrix itself here, we have this Fmn, is Hermitian if it's complex conjugate, of course, and if we were to flip the indices, or take the trace of the matrix. So another way to write this would be, not the trace, the transpose would be the transpose, and of course these also It doesn't matter which way you do it. But essentially, that's our new definition for the matrices in the Hermitian kind of form. Okay, so it's going to be the trace, or the transpose of the complex conjugate. Okay, and so the diagonal elements. Okay, the diagonal elements, of course, f and n are real, and they have to be because they're the expectation value of f in the stationary state n. Okay, so that's really all we have to do for matrices. But now we need to describe how these matrices then transform. Okay, so how does a Hermitian matrix transform? How can we describe an arbitrary transformation of a Hermitian matrix? Well, first of all, it's got to remain, and the probability has to be conserved, of course. And so we're going to have to, encode some kind of relationship. We're going to have to suppose some kind of relationship that allows us to transform between these Hermitian matrices. And so let's just let psi n be related to, or psi prime be related to some state psi. But what we're going to have to do is say, okay, they need to be related by some kind of operator that allows us to transform between those two bases. Okay, and so the unitary operator, we're going to call it a unitary operator. It's going to be that s hat, or s dagger times s should give us 1. Okay, and this is going to be the first imposition that we're going to do that ensures the new basis is also orthonormal. Okay, and so the matrix elements on the operator f and the new basis are related to the matrix elements in the transformed old basis, and so we can then call this new fmn, f prime, okay, which is just going to be, of course, defined by psi prime, which is not the derivative, it's just the transformed basis, okay? So this is a new basis that we have, dq, okay? Same coordinates, just a new basis. But we're going to relate this in such a way that we have the old basis, fn, I'm sorry, this should be n, okay? Give the old basis times the s dagger hat with this operator here, which gives us this new kind of way to represent or to have the physical quantity in the energy representation. All right, and this new representation of the matrix now, we can define the operator here then really. To be that we have this operator to be the inverse of the unitary matrix with the old operator that we have in the old representation. Okay, so we can transform to this new we can transform to this new operator, or this new way of representing this from the old by taking the inverse of the unitary and the operator here acting on this other unitary matrix. It's going to have this special property. And so also, just to note, the trace of the matrix, so let's say trace of the operator is going to be, of course, defined by the sum over the nth, or just over the diagonal components of the matrix, and they're going to be invariant. So are invariant under any transformation. Okay. Oh, sorry. Under unitary transformations. Okay. That's what we're defining this. So now we can then move on from this idea of unitarity to the Heisenberg representation of operators. So we have the energy representation. Now let's look at what Heisenberg kind of cooked up for us in this. Look at what Heisenberg cooked up for this in this representation of quantum mechanics. Okay, what did he derive? Well, he told us that we can do something really cool. Okay, so in the Schrödinger picture, of course. In the Schrödinger picture, operators are time independent, okay? So operators are time independent. Okay, they're time independent. And so in the Heisenberg picture, though, okay, the Heisenberg picture, the state vector is fixed at some initial t. Okay, state vector is fixed, which is also happens to be psi, right? So we're defining this as a state vector now. And so it's fixed as an initial t, at an initial time t, but the operators can evolve. The operators are allowed to evolve because of unitarity, okay? And the Heisenberg picture is defined as the operator varying with time is equal to the unitary transformations, which are going to look something like e to the I, the Hamiltonian, times t, with the acting on the operator, also with the negative complex conjugate of this, t, acting, the operator acting on this, and this is going to allow us to then find its equation of motion, right? Another equivalent class of the Heisenberg equation of motion, but this time it is a total derivative. Actually, I think it was a total derivative before, but we then have IH bar is the commutator of this changing operator, where we fixed the time at t equals 0 and then changed it, okay? And allowed it to go on. So we have this kind of Schrodinger equation where we're fixed time independence, and here we're allowed, time is allowed to evolve, and it has to change unitarily, okay? Next, let's talk about density, all right? Just making sure I still have time. All right, let's talk about density. So let's say we have some larger system, okay? Let's say we have some larger system that is a closed system that's large, okay? A larger closed system that contains within it a smaller system within it. But this larger system may not have its own wave function, and so it's entangled with the rest of the system. And so we would call this a system mixed state. So it's a mixed state. And we have to represent it with a density matrix. Okay, so let's let the total system coordinates, okay? The total system coordinates are going to be represented by Q and X for the part that's inside of the system, okay? Our subsystem. So let's say this is our subsystem, the coordinates of our subsystem here, and this is the coordinates of our whole system, all right? And so there's something within the whole system, X, okay? And so what we're going to say is the total wave function of this should be a function of both of those coordinates, okay? It should be a function of both of those coordinates, and that the density matrix is going to be defined, so let's call this rho for some x prime for the subsystem. X prime is going to be our integral over that wave function, right? So we have the wave function which contains within it the coordinates, or some state that contains within it the coordinates of our total system, and then the subsystem that's within it. And we can also have the complex conjugate of it, and then we're going to integrate it with respect to this kind of, I guess, dummy variable, okay? Or some, not a dummy variable, but the variable that we're integrating with respect to. And I'm sorry, this should also be Q. We're still working in Q, in the general, the probability distribution, the configuration space of the whole total system, okay? So there's just something within it. All right, and now the mean value of the operator then is going to take on the value, or is going to take on the trace, is going to be described by the trace of the density operator. Okay, we're defining a density operator in such a way that the mean value of it is the trace of the density operator acting onto the physical operator. And this is going to be given, or this is going to be given by the operator acting on the density matrix x and x, p rho of x and x prime evaluated such that x is equal to x prime and integrated over x, okay? And so when we do this, a wave function then can be formally, so we have the mixed state, but we can formally describe a pure state. Okay, we can formally describe a pure state for which the density matrix has this special form, of course, where it is non-interacting. This is why it was really important to watch my conceptual video, but where the wave functions are non-interacting with each other. And so this would be a pure quantum mechanical kind of state, and this state would be mixed here. Also for a pure state, it has this property where the operator, the square of the operator, is the operator itself. It should be quite, you can verify that for yourself. But also for a mixed state, the trace of the operator squared would be less than 1 for a mixed state. And so what we can then do is say that the time evolution of the density matrix, so the time evolution of the density matrix, del by del t of the, the density matrix with, I guess we're formulating it in the operator kind of representation, of course, but the operator will satisfy the operator equation, okay, which then encodes the density matrix, but this should be equal to the commutation of the Hamiltonian with the density matrix itself. And so this is called the von Neumann equation. This is a central result here. Okay? This is the von Neumann equation. There's just the temporal derivative, or the time evolution of the density matrix. Okay, given in terms of the commutator. So all of these important kind of conservation laws can be recasted, right? Or at least the conservation laws with energy can be recasted and reframed in this quantum mechanical way. All right, with this, and the commutator keeps showing up everywhere. And so now let's talk about momentum. So we're going to derive momentum. We're going to derive it from the principle of symmetry, which comes from Noether's theorem, that for a closed system, space is homogeneous. Okay, so space is homogeneous for a closed system. This is a classical principle. Okay, and we're going to re-employ this in the context of quantum mechanics. Okay, so that means that the system's Hamiltonian operator is invariant. Okay, it's invariant under arbitrary spatial transformations. Okay, so for nabla. All right, so an infinitesimal translation by a vector, let's say dr. So this is an infinitesimal translation. Okay, infinitesimal translation dr. And it's by a little vector. Okay, this is a little vector, and it forms a function. It'll form this function dr into psi r into psi r plus little dr. Okay, so little vector. It's going to increment it, and so if we were to Taylor expand this, this would be the first order term here dotted with nabla acting on psi. Okay. And what we can then do is say, okay, well, we can factor out the little r here with the dot product of nabla, and so this, of course, would also be an operator. And guess what this operator is called? it is called something very logical. It is the infinitesimal translation operator T of dr. All right, and of course, because it's an operator, it's a hat, okay? So that is the infinitesimal translation operator dr, and so of course, this must be true because we're showing that it must be conserved, etc. But also, here's the thing, dr is just a constant, okay? It's a constant vector. And so this condition is just going to, as we initially supposed before, it's just going to be the commutator of the Hamiltonian with nabla, all right? And so since we want to use this kind of quasi-classical limit now to derive what we want from this, and so it's going to be approximately this times the action, of course, divided by h bar, and well, also for the classical momentum, how we define momentum classically in the context of Hamiltonian is it's the gradient of the action, all right? And so what that'll allow us to do is to test this hypothesis, okay? Let's say that we have an operator, okay, that an operator that must be some constant times nabla, all right? This hypothesis is the operator must exist that there's some constant times nabla. All right, so hopefully you get this here. You get that. Oh, we just did all of that reasoning just to arrive that H is invariant, of course, with the nabla, the commutation between Hamiltonian and nabla. All right. And so this is our hypothesis. Should there be an operator that we can then get in the form of the momentum so that we can make an operator equation, all right? And so in order to do that, we'll say, all right, we'll suppose that there should be some unique operator that exists for momentum, that exists as such. It'll be this nabla that acts with some constant on the quasi-classical limit, all right? And when we get the quasi-classical limit, this will then look like the IH bar of the nabla of the action times e to the ISH, okay? And then what we can then do is simplify this out so that we have ICH is equal, or sorry, ICH times the gradient acting on the action times, of course, this is just psi again. And then what we're going to have then is that we have ICH bar times momentum. Look at that. We just got momentum out of, from my hypothesis, right? Momentum came out of the wave function. And so all we need to do for this, we need this to be true, right? Psi. We need this to be true in some sense, right? If we want this operator to be true, then we have to set this quantity. We have to set this quantity equal to 1. Do you see what the logic of that is? So that this operator equation that I'm forming out of acting onto the wave function spits out the momentum, right? Now, I hope that you really see like us solving this operator equation and setting this equal to 1, so that C is necessary, that C then is uniquely negative IH bar. And so then thus the momentum operator is equal to the negative IH bar times nabla. What a weird form, but that's kind of what happens, okay? And so we can also deduce that the eigenfunctions for the wave function will take on this form where we have the dot product of the momentum with the position of where you are with the wave, and that these are actually what we know to be in electromagnetism as plane waves. And so the eigenfunctions for momentum happen to be plane waves. Okay? Whenever we want to observe momentum, we get plane waves. And this is why we can see that there's going to be, or we can anticipate some incompatibility with some incompatibility with measuring both momentum and position in the same single coordinate. All right? Because of this plane wave these plane wave eigenfunctions that'll give you the momentum. So let's look at this, okay? All right. So the operator then. So we are going to say that the position operator is this, and that the momentum operator in that, with respect to that same coordinate that we are interested in, okay, it's going to be the derivative of that coordinate. And so we can then try to, I guess, kind of calculate the commutator and see if anything is conservative. And so we can test this out, try to do the measurement, okay? And so we'll have IH bar times x phi del x, okay? And then all of this is going to equal IH bar x del by del psi of x plus IH bar psi plus IH bar x del psi is equal to that. And then those cancel out, as you can see. We can have IH bar, IH bar psi. Okay, so this is all equal to IH bar psi, the commutator. And oh, I totally forgot. We're doing the commutator acting onto the wave function to see if we can do both of those things. And we're going to get out an imaginary value, okay? And similarly, it's the same for y and z. Same thing here, y and z hat, you know. This same result kind of happens. But operators for momenta along a different axis do commute. And hence, you know, they do conserve the probabilities and the Hermitian statistics. Okay, and so what we now need to do is figure out something, which is a result. You're gonna use a result from Hermitian statistics. This is a theorem. All right. Double check this. This is a theorem. Okay. General theorem. Which is that if I have the variance of some quantity A and the variance of some quantity B, the uncertainty of that variance, or the uncertainty of those quantities, is bounded. Is bounded by the magnitude of the operator, the expectation the expectation value of the commutator of those operators, where A hat and B hat are Hermitian. Okay? So this is a general theorem. And of course, for the definition of variance, we have the square of the variance. That better give us the expectation value of the operators minus the expectation value of the operator itself, quantity squared. Okay, so I kind of read that kind of jacked up, but hopefully that kind of makes sense for you to see. And so what we can do then is try to do this for some position and for the uncertainty of the momentum in the x direction. And we can employ this theorem and kind of borrow it, which is the expectation value of the commutator. And of course, we know what this result is, this commutator, because we computed it previously. And so this is going to be, of course, IH bar, and we'll have the magnitude we'll have the magnitude of the of IH bar, of the expectation value of IH bar, but the expectation value of IH bar is not. I mean, it's not inherently real, and so we just want the magnitude of this. So it's going to be H bar over 2, and so we'll then have this, and hence this is something that we know, or that we call the Heisenberg uncertainty principle. So it took us a while to get from general uncertainty, or the general uncertainty principle, to get this formal kind of Heisenberg's uncertainty principle, which encodes a lot about it. It encodes a lot about momentum, and encodes a lot about momentum and conservation laws, which we had to define momentum operators from all of these, from this theory that we developed previously. But what this is going to allow us to do is basically give us a inequality. What this physically means, right? We're going from the mathematics of the variances to or the upper bound, the lower bound on the statistical accuracy that we can have for Hermitian operators. This is a purely mathematical relation, but we're then relating this to actually the particle's position, so that if it's known with high precision, if this goes to 0, right? So if this is going to 0, this is going to go to infinity. All right? And so the uncertainty of the momentum, which makes logical sense, is going to go up. It's going to go up. It's going to be a perfectly kind of localized particle, as we were talking about, right? It's going to look like a delta distribution, okay, or a delta function in space with a definite momentum as a plane wave. A delta function is a superposition of all the possible momentum plane waves, okay, that with an equal weight, okay. And so conversely, if a particle's uncertainty goes up, we don't know where the heck it is, and we know exactly what its momentum is in terms of the plane waves in that position, or in terms of that momentum. Its position is completely unknown. All right. And so a state of definite momentum is a plane wave with is a plane wave extending over all of space. This momentum that we know for certain is a plane wave extending over all of space, where the position or the distribution of the position is uniform. So that means that the uniform probability of position, it could be anywhere along that plane wave. Okay, so we have no idea where it is, and so that's kind of the real physical interpretation of Heisenberg uncertainty principle. You have to view it in the sense of these of a more specific coordinate. All right, that we're taking the momentum of. It's not just general momentum, because we can measure plane waves in another axis and have the exact position. Okay, that's theoretically possible, or at least uncertainty is bounded up to h bar over 2. And so this is basically the most quantitative foundation of ideas that we introduce in the first episode. So this shows that just this classical concept of a trajectory, again, requiring definite x and momentum sub x simultaneously, is untenable in quantum mechanics. So thank you for watching, and we'll see you next time. Bye-bye.